Hello, I'm Bhav Ashok, the author of Architecture Compression. Architecture compression is a gradient descent-based approach for discovering efficient architectures. Before we jump into the actual method, let's take a look at some of the prior approaches in the space. The most popular approach is to use reinforcement learning-based neural architecture search. The basic idea here is to sample an architecture from an RNN, train this architecture to get a reward, and then use the reward to backpropagate through the CNN using the reinforce algorithm. This is an effective approach and has been proven to be state-of-the-art in multiple benchmarks, but it's a black box optimization over a discrete architecture space, which results in sample inefficiency. An alternative which was proposed to alleviate this issue was a differentiable NAS, which basically relaxes the problem from a discrete to a continuous search space and performs gradient descent there. And then it discovers cells and it stacks these cells to form the final architecture. This approach is efficient, but it's also a local optimization over a single cell. And if we want to discover our efficient architectures, we would like to use a more global optimization over the entire architecture to account for the task-dependent differences at different levels of the architecture. So this is where architecture compression comes in. Here's a high-level overview of the approach. So we start off with a discrete architecture space shown on the left here, and then map this to a continuous continuous latent space shown in blue here, which is then used to predict the parameter count and accuracy of the architecture. So once this latent space is trained sufficiently well to encode the parameter count and accuracy of a given architecture, we then use this to perform compression. So during the compression step, we start off with a known performant architecture, let's say, for example, VGG inspired architecture, and then get the latent code from our encoder, and then use a specified parameter count and accuracy to perform gradient descent on this feature. The final feature after gradient descent is then decoded to a compressed architecture. On the bottom here, you can see the representations we use for the discrete architecture. The layers are represented as a simple vector of the hyperparameters of that layer. In this case, it's layer type, kernel size, number of outputs, and so on. And the architecture representation is just a lengthwise stacking of these layer representations. So that's the high-level overview. This is the actual implementation that we used here. So we used a 1D convolutional encoder and decoder to map the architecture to and from the continuous space. And then we used a two 1x1 1D convolution regression towers to go from the feature space to parameter count and accuracy respectively. This whole system was trained with 1,500 randomly generated architectures so that we could learn a rich and informative latent space to be used for compression. The next slide here shows you what actually happens during the compression step. So this is a visualization over 7 steps of gradient descent on our latent space. We start off with a base model, which is a CNN trained on CIFAR10, and then we perform several steps of gradient descent. So on the left here, you can see the compressed architecture at each iteration, as well as on the right here, you can see the parameter count and accuracy of each of these generated networks. As expected, the parameter count decreases as we perform more iterations, while the accuracy remains somewhat consistently close to the original architecture. So we ran a few quantitative experiments on popular image recognition benchmarks such as Fashion MNIST, CIFAR10, CIFAR100, Street View house numbers, and saw anywhere from a 5x to a 20x compression with a negligible drop in accuracy. And so while we have some initial promising results, there's still a lot more that can be done in this space. I think large-scale experiments is something that should be tried. We can also incorporate several hardware constraints, such as latency and power consumption, and also run this on more complex architectures, such as ResNets, DenseNets, Inception Nets, things that have skip connections, and so on. So with that, I thank you for listening and invite you to ask questions in the Q&A. Thank you.